Alright, so far we have talked about parametric tests such as one sample t-test, two sample t-test, which could be unpaired or paired t-test, ANOVA, and Pearson correlation. So parametric tests are powerful tests for making inference about population parameters, but they are based on multiple hard-to-meet assumptions. For example, one of the most important assumptions of the parametric test was normality of the data. In the previous video, we learned that we can check normality of data visually, for instance, using QQ plots, and also statistically, such as using Shapiro-Wilk and KS test. If the normality assumption couldn't be met, in other words, if the distribution of the data was skewed, one main solution was using non-parametric version of the test. So non-parametric tests are also called distribution-free tests, and the data doesn't have to follow normal distribution or any other distribution. So you can also use non-parametric tests when you have a small sample sizes or outliers in your data, or sometimes your data are in nominal scale or ordinal scales. So in that cases, it is preferred to use non-parametric tests than parametric tests. For instance, in surveys or questionnaires, some questions might be to rank some choices in ordinal scales, such as from low to high, or never, sometimes, often, always, or I don't know, strongly agree, neutral, disagree, strongly disagree. So in that cases, in ordinal data, the only option that you have for analyzing this kind of data is using non-parametric tests. So when do we use non-parametric tests? When the normality assumptions couldn't be validated, the data had a skewed distribution, or when you have a small sample size, less than 30 observations, so it is better to use non-parametric version when there is outlier in your data set, and when your data are nominal or in ordinal scales rather than interval or ratio. So the main advantage of non-parametric tests is they can be used for a wide range of data types, and because they can also be used for the continuous variable and also for the nominal ordinal data. So they can be used for a wide range of data type and also for a wide range of applications, such as analyzing ordinal data when there is some outliers in the data, when the distribution doesn't have to follow normal distribution. In most cases, the distribution is a skewed distribution. Most cases, the sample size that you have has very small size, or there are some outliers in the data. So non-parametric versions in those cases are preferred. So because non-parametric tests make less assumptions about distribution of data, and sometimes non-parametric tests can be your only options for analyzing the data. However, the main disadvantage of non-parametric tests is, compared to the corresponding parametric tests, they are generally less powerful because you are losing some information when you use non-parametric tests. So in other words, parametric tests are more likely to detect the true difference if the distribution is normal. So if the distribution is normal, it is highly preferred to use a parametric test. So in this video, we will apply 4 main non-parametric tests to solve real-world problem in R, and then we will interpret the findings. So here is the list of parametric tests and also the non-parametric alternatives. For example, for one sample t-test, the non-parametric version is a sign test, or Wilcoxon signed rank test. And for paired t-test, the non-parametric alternative is again signed Wilcoxon signed rank test. And this is because, as you remember, for paired t-test, after you calculate the difference between the two paired group, it becomes like one sample, right? So the difference is just one sample. So one sample t-test and paired t-test, both of them, they use Wilcoxon signed rank test. So for unpaired t-test or independent t-test, the non-parametric version is Mann Whitney U test, or is the sum test, or Wilcoxon sum rank test. for all of these three, we use the same command in R programming language. So the calculation in R is super easy. The next one is one-way ANOVA, and the non-parametric version is Kruskal Wallis test. And finally, Pearson correlation, and the non-parametric alternative is Spearman rank correlation. But the last one, we have talked about the last one, Pearson correlation and Spearman, in a separate video because it's more about the correlation. So let's begin with one sample t-test in R. So in our studio environment, let's make a comment that shows the purpose of the study, which is to practice non-parametric tests. So we want to start with the one sample t-test, okay? So, or the non-parametric version, which was the Wilcoxon signed rank test. So I use one sample. So if you remember, the purpose of one sample t-test was to compare one sample mean with a hypothetical population mean or any hypothetical value. So we wanted to see whether the sample is significantly different than the population, significantly lower, sample mean is significantly lower, higher, or just significantly different, right? So for the Wilcoxon signed rank test, it's going to be the same, but instead of mean, we use median, okay? So we want to see whether the sample median is significantly different than any hypothetical value, okay? So before talking about that, I think it's better to install the ggpop-r that we talked about, this package in the previous video about the normality check. So we use this package to create the QQ plot to test the normality, okay? So we use install.packages, and here within the quotation we type ggpop-r and then click run. And after that, you need to load this package using library command, and then just mention the name of the package, ggpop-r. You don't need to put that in the quotation, and then click run. So now I'm going to load the data. Okay, so this is for one sample non-parametric test, so NP test. So I'm going to load the data, and I'm going to use the built-in data in R. So if I use data command and then click run, it shows you the list of built-in data set in R, and one of them is CO2, which is carbon dioxide uptake in grass plants. So if I type the or I can select it from here, which was CO2, and then click run. So here, if you double click on that, so this data set shows the carbon dioxide uptake in grass plants for 6 different type of plants. Okay, so 1, 2, 3, 4, 5, 6. That's are in 2 locations, in Quebec and also in Mississippi. And we have the concentration of the CO2, and also we have the uptake or carbon dioxide uptake for these plants. So the first thing that we want to do, we want to use this data set for running a couple of non-parametric tests. Okay, we can use that for one sample t-test, unpaired t-test, and also for ANOVA. So we want to use that for 3 different non-parametric tests. So the first step is that we have to check the normality of the data. Okay, check normality. And if you remember, for checking the normality, we use both visual technique and also the statistical technique. For the visual technique, we use ggqq plot, and here we type the CO2, which is your data, and then from $, we want to look at the uptake. And here, if you click the run button, it shows that you can see that the distribution is not close to this reference line, right? The dots is not close to the reference line, so it shows that the distribution, it seems like the distribution is not following a normal distribution. And also you can use Shapiro Wilk test. And again, if you, let me copy this. And if I run the Shapiro test, you remember that if the p-value was less than 0.05, it shows that the distribution is non-normal. So we're looking something that is greater than 0.05. But here, if you run the test, you can see that the p-value is less than, it means that's significant, which means that the distribution is non-normal. So it is better, since the distribution is not normal, so it's better to perform non-parametric test. Let's have an imaginary example that, let's say a scientist believe that the median CO2 uptake for these places, for Mississippi and Quebec, is less than 30 at the population level, okay? So we want to test this hypothesis, okay? And since it's a comparison of one sample with any hypothetical value, which is 30, so we will use one sample Wilcoxon signed rank test. We will use the non-parametric version of the one sample t-test, okay? So the null hypothesis is going to be the median uptake, CO2 uptake is 30. I honestly don't know the units for this variable, but the alternative hypothesis, which was the argument for the researcher, was that the median uptake is less than 30, right? So we have to run the Wilcox test, and it's very simple. It's Wilcox.test, and here you just mention the variable that you want your sample, which was CO2 uptake. So if you look at the variable, so here is the CO2 uptake. So we want to compare this sample with population. It's a one sample t-test. So, and I want to compare it with the value of 30, okay? And since the alternative says it's less than 30, so alternative has to be less, right? So if I click run, so the value that I get here is p-value is 0.01, which is less than 0.05 at 95% confidence level. So we reject the null hypothesis, okay? So which means that we reject that the median uptake is 30. So we accept the alternative. We accept that the median uptake, median CO2 uptake is less than 30 at the population level. Okay, so that was for one sample t-test using the non-parametric test, using the Wilcoxon signed rank. So now I want to compare two samples. So in this data set, I want to compare Quebec and Mississippi, right? So there are two different samples, and so it's definitely is an unpaired t-test, right? So, or independent t-test. So I want to, so the next one is two sample or unpaired, but I want to use the non-parametric test, and we will see why we have to use the non-parametric test. Let me create the box plot for CO2 uptake, but I don't want for the entire uptake. I want to separate it by the type, okay? So I want to separate it by CO2 and $ type, so by city, right? So for Quebec and also for Mississippi. So you can see that there are multiple outliers in the Quebec according to the box plot. And so that's one reason that probably non-parametric test is good. But also I think that the distribution, so you know that for the unpaired t-test, the distribution for both groups have to follow normal distribution. But I don't think the distribution here is follows normal distribution. So let's check it. So let's check the, for example, for Quebec. So I want to, for Quebec is record number 1 until number 42, right? So I want to, let me just select the cubic, and I want to, from CO2, I want to select the all rows, rows 1 to rows 142 and all column, okay? And then I save it in the variable Q. So if I look at that, it's only for the cubic, right? So now I'm going to look at the QQ plot for the cubic. So GGQQ plot for the cubic, which column for the uptake? So I want to compare the CO2 uptake. I want to look at the normality of the QQ plot for the uptake for only for cubic, right? So if I click run, so it shows that, as you can see, it's too far from the this line. So it shows it's very obvious that the distribution is not normal. We can also use the Shapiro test. And again, if you look at this value, the p-value definitely, I think that it's going to be less than 0.05. So it shows that the distribution is not normal, okay? So that's another reason that, so there are outliers and also the distribution is not normal. So it's better to use the two-sample non-parametric version on unpaired t-test, which was Wilcoxon rank sum test or Mann Whitney U test, okay? So again, it's very simple if I want to run that, but let me mention what are the null hypotheses. The null hypothesis is that the median CO2 uptake is for both cities, for Mississippi equals to cubic, right? Or the difference of the median CO2 uptake for both these cities is 0. And the alternative hypothesis states that, I don't know, it's up to you. So we can say that the median is, I want to use the two-sided test. So median CO2, these two cities is not equal, or their difference is not 0, okay? So again, we use the Wilcoxon test. So the name of this test is Wilcoxon rank sum total, which is also known as Mann Whitney U, okay? So again, the formula is similar to the other one, Wilcoxon test. So you have CO2 uptake and then separated by type. So you have two different groups, so group 1 and group 2. And also it's not a paired test, right? So we set the paired argument to false, right? So let me run the test and see the result. So here is the result for the Wilcoxon rank sum test, which is also a Mann Whitney U. And here, if you look at the p-value is very, very small, which means that's the CO2 uptake, which means that we reject the null hypothesis that the CO2, the median CO2 for both cities is equal. So according to the result, the median CO2 uptake, so we have to accept the alternative hypothesis because the p-value is less than 0.05. So the median CO2 for these two locations are significantly different from each other. And here we got a warning that the RR cannot compute the exact p-value because there are some ties, right? To address this issue, we can set that we don't want to calculate the exact p-value. An approximate value for the p-value is also okay. So here, if you type exact and set this to false, and if you click run, so you will not get that error, okay? But if you compare these p-values, again, still they are they are the same, so it doesn't have any influence on our result. The only difference between the unpaired t-test, non-parametric, and paired t-test in the R is that here for the paired t-test you have to set the paired as true. That's it. That's the only difference between these two, but we will also solve the problem. So the next one is ANOVA, okay? So ANOVA non-parametric version, right? NP test. So we know that we used one-way ANOVA when we wanted to compare 3 or more population means, okay? So here we want to compare uptake, but for different type of plants, right? So if I create the box plots, So box plot of the CO2 uptake and separated by from CO2 for the plant. So if I create the box plot, so if I now click to zoom, I can see that 1, 2, 3, 4, 5, 6, that's for Quebec, right? 6 different type of plants, and also 1, 2, 3, 4, 5, 6. And if you look at the plots, so there are many outliers in this data set, and also the distribution apparently is not, doesn't follow a normal distribution. Again, you can use the QQ plots or Shapiro or KS test to, and you will see that definitely the distribution is not normal. Okay, so the null hypothesis here, if you remember from the ANOVA, was that all of the means of the CO2 for all of the groups were the similar, right? So here the median of the CO2 uptake for all are the same, okay, are similar. Medians are not. So another one, the alternative hypothesis here states that at least one of them is different, right? So some medians of CO2 uptake are different. So again, according to the, if you remember from ANOVA, ANOVA doesn't tell you which one is different. If you could reject the ANOVA, ANOVA can tell you whether they are different or similar, okay? Cannot tell you exactly which two tests, which two groups are different than each other. So the test that we will use is Kruskal-Wallis test, right, for the non-parametric version, because the distribution, according to this, there are so many outliers, and also you know, the distribution is not normal, because box plot also can tell you that the distribution is not normal. So, and for Kruskal-Wallis test, you are going to, we can use this one, right? We want to have the uptake separated by plant, right? And then if you click run, what will happen? So the Kruskal-Wallis ranks some tests, and degree of freedom is n-1, number of group -1, which was 12-1. And if you look at the p-value, is very, very small, right? Which means that it rejects the null hypothesis. It rejects that the median CO2 uptake are similar for all of them, right? So at least one of them is different than the others. And again, similar to one-way ANOVA, the test doesn't tell you which pairs are different from each other, and we need to run an extra test. So for this one, we use pairwise Wilcox test. And for the pairwise Wilcox test, so you have to use, so the, if you look at the, let me look at help for this one. So pairwise test, first of all, for X is your response vector, which definitely is your CO2 uptake, and you have to separate it. So for the grouping variable, you shouldn't use the tilde like this. We have to use comma for the grouping variable, and also we have to set the p.adjustment method. And for the p adjustment method, there are multiple tests, multiple techniques, but the most important one, or the most widely used, is Benjamin Hodgberg or VH technique. So we want to use that one for comparing the pairs, right? So first of all, we have CO2 uptake. According to the help of the R, we have to use comma, right? And then we also have p.adjust method. So here, if you type BH, right, and then when you click run, what will happen? It will compare all of the groups to each other, okay? So if the p-value was less than 0.05, we can say that these are significantly different from each other. For example, MC2 and QN1, right? So if you look at that, MC2 and QN1, MC2 is here, QN1 is here. So the median sounds like the median are different from each other, right? And here we don't have MC2 and QN2. So MC2 is here, QN2 is here. So the median is significantly different from each other. And so yeah, you can compare which two groups have the different median according to the post hoc. It's like a post hoc test for the ANOVA, right? Pairwise Wilcoxon test. So the last one, so we talked about one sample, we talked about unpaired, and we also talked about ANOVA. How about the paired t-test? As I mentioned, it's very similar to the unpaired. The only issue is that you have to set the paired as true in the paired t-test. Okay, so paired NP test. So we can't use that because it was used for the before-after studies. So in this data set, we don't have that, before, after, or pre-test, post-test. So I want to use another data set. So the data set that I have is called hypnotism. So they have measured the pain for 8 different people before hypnotism and after hypnotism. So you can easily create this data in your own RStudio. Here is the sample size is very, very small, right? So the non-parametric version seems a better option, okay? So I want to read this data set in RStudio. Okay, so I want to use, because it was a CSV file, so I want to read this data, read that CSV file, that choose, and I want to set the header to true, and I will save it in a variable called data, right? So I saved it in my hypnotism, and so here is your data set. So 8 people before and after, right? So the next step is that, so the null hypothesis here states that the median of the difference of the pain, so because the values here are pain, right? So I want to compare the median of the pain before with the median after, okay? So in the null hypothesis that the median difference is 0, right? So the median difference in pains is 0, or the median pain before equals to median pain after. And the alternative hypothesis states that the median difference in pains is not 0, okay? So you can say that it's reduced or increased after the hypnotism. So it's up to you how you want to test it. I want to use a two-sided test, okay? So it's not 0, okay? So after that, again, we use the Wilcox test. So we have the data for, we want to compare 2 classes with data for before and data after. And here it's very important that you have to set the paired to true, okay, because it's a paired non-parametric test, which was the Wilcoxon signed rank test, because it converts the paired t-test to one sample t-test, right? So if you click on run, it shows you the Wilcoxon signed rank exact test. And if you look at the p-value is 0.01, which means that it rejects the null hypothesis. It rejects that there is no difference between these two. And there is a difference, which means that it's probably increased or decreased, so which means that the hypnotism was effective.